Okay, welcome back. And I left you with the optional exercise to solve this equation in the special case when we have no emission. So this is just a differential equation. We can rearrange the equation to bring the terms in I over to the left-hand side and bring the optical depth term over to the right-hand side. So sort of separation of variables for those of you who remember your simple differential equations. And so that's what I've done at the top here. So we've now got di over I equals minus d tau, and we can just integrate both sides. So the integral of 1 over I is just the natural log of I, and the integral of d tau is just tau. We're bringing the minus sign with us. As always, there's a constant of integration, which I'm going to characterize here by an initial intensity again, coming into the medium. Again, not too worried about that. The idea here is that, if you then take the antilog of both sides, then you've got I nu, which is what we wanted on the left, and we've got this e to the minus tau nu factor on the right-hand side. So you can see that e to the minus tau nu describes the idea of the attenuation of radiation as it travels through a medium. So exemplified by this little example curve on the bottom here. So you start off with some intensity, I naught, and as you go further and further through a medium, the intensity exponentially decays depending on the value of the optical depth, okay, which obviously depends on the opacity of the medium. And so, you can imagine in the lab, you might shine a light, a white light through some sort of colored solution. And, and the more and more solution you have, the fainter the signal is looking through the medium on the other side. That would be an example of this type of behavior. So you can see e to the minus tau is like an attenuation factor due to absorption processes in a medium, and applies just as well in astrophysics. Just a quick note that I used the term absorption there, but of course we talked about absorption and scattering processes earlier. You will also hear another term called extinction, and extinction is the sum of those two terms. If you've got a medium that both absorbs and scatters, then really the optical depth and the opacity is dealing with the extinction processes through those media. Okay, let's move on. So let's now I'll just return to this solution here. So we've got a 1 to the e to the minus tau factor on the right-hand side here. And you've got basically two extremes that you could consider here. So as I mentioned before, if tau is much, much greater than 1, then this e to the minus tau factor is going to tend towards 0. So if tau is much greater than 1, then I nu just becomes S nu. Okay. And conversely, if tau nu is very small, you can look at the series expansion of e to the minus tau, which will basically just be 1 minus tau plus higher order terms. And then in that case, this would just become S nu times tau nu. Okay, so that is what is on this slide here. So if the medium is very optically thick, okay, so remember I was talking about that if the optical depth is much, much greater than 1, then effectively the intensity that you see is just the source function, okay? And more accurately, it would be the source function at the location where the optical depth went above unity. Okay, so you see into this source, but you just see a kind of a surface, if you like, radiating where the optical depth is 1. You don't see any further. If the medium is optically thin, so tau is much less than 1, you can see all the way through it. And in a sense, the amount of radiation you get will just then depend on this value of tau. So if you get a lot less, if you've got a lot less medium, then the intensity will be smaller. Okay. Okay, so now let's have a look at this idea of the source function for a moment. And again, we'll take a special case where let's assume that our medium that we're talking about is now in what we would call a thermal equilibrium. So that means that the conditions in the medium are well defined by the temperature of the medium, and that every kind of process is balanced by its inverse process. So the absorption of photons will be balanced by a re-emission of photons, that kind of thing. Basically, the condition of the material, the temperature of the material is well balanced with the radiation field itself. They are in the equilibrium. So if that's the case, we have this special case where the source function is actually given by the black body Planck function, okay, which I'm calling B nu here. Okay, so remember the Planck function again is this special case where you have a perfect absorber or a perfect emitter, and that comes from the kind of black body assumption. Okay, so again, if we had a basically a star is a pretty good example of this. So the material, the gas at the surface of a star is pretty close to thermal equilibrium. And when we see into the star in the sort of optical regime, we see into where the optical depth is about unity, and the emission that we see is basically very similar to that of a black body. So that is a good example of this condition. But we're interested in radio wavelengths, so very, very long wavelengths. And so again, if you're familiar with how the Planck function works, then at very long wavelengths, we can use what's called the Rayleigh-Jeans approximation for the Planck function. So the Planck function, which normally is sort of, has a complex sort of exponential factor in it, simplifies down to this equation instead. So this is the Rayleigh-Jeans approximation for the black body function. And so this is true when basically h nu is much less than kT. So when we have low frequencies, basically, which is what we do in the radio regime. Okay. So you can see that it just linearly depends on temperature here. And it depends on nu squared. So the Rayleigh-Jeans approximation is used a lot in radio astronomy because we're always operating effectively in the Rayleigh-Jeans approximation, because we're always operating at such low frequencies. And you can see from that sort of previous equation, if the intensity is equal to the Planck function, then it effectively is proportional to temperature here, so that the intensity would be proportional to temperature. Apologies for the beeps. So this comes to this concept that is used a lot in radio astronomy, that you can use a temperature as a measure of intensity. Okay, and this brings in this idea of the term brightness temperature, okay, often referred to as T sub B. So this is the temperature a black body would have to be in order to give the same intensity, I nu. Okay, so here we're going that full way. So assuming that I nu is given by the source function, is given by the Planck function, which is given by this Rayleigh-Jeans approximation. So we're cutting out all of those things in the middle to just say that the intensity is proportional to this brightness temperature, or another way, we can use this concept of brightness temperature as a measure of intensity. So if we do this, we can kind of rewrite the radiative transfer equation that we had before. Instead of using intensity and source function, we can use brightness temperature to represent intensity, and we can use the actual temperature of the gas instead of the source function. And so that is what I've done here. So instead of I nu here, we now have brightness temperature. And instead of the source function here now, we have the temperature of the emitting material. Okay. So now we have two interesting cases. So again, in the optically thick case, if we measure a brightness temperature with our radio telescope, okay, because it's a way of characterizing the intensity of the radiation, if we know our medium is optically thick, then we are exactly measuring the temperature of the gas we're looking at. Okay. So you'll see into a medium, into its optical depth 1 surface, it'll effectively be radiating as a black body at a given temperature T at that point. And then the brightness temperature will directly tell you the temperature of the gas, if you're in this situation. If you're in the optically thin situation, then your brightness temperature will be a lot less than the temperature of the gas that you are observing. And that's because it'll depend on the optical depth, which will be much less than 1. Okay, and we'll be putting some of these into effect in the workshop associated with this lecture. Okay, so just to summarize, so the opacities determine how photons interact with matter. So we've had all these different types of processes: absorption, bound-bound, bound-free, free-free, and then we've had scattering processes like Thomson scattering. And we've defined these quantities of opacity and emissivity and source function in order to derive a radiative transfer equation that we can use to predict the intensity of radiation that we would observe given the physical conditions of the gas that we're looking at. And you can really think of the radiative transfer equation as the connect, if you like, between sort of theoretical astrophysics, where people would be building a mathematical model of astrophysical phenomena, and the observers who observe the intensity of radiation. Okay, and the glue between those two is the radiative transfer equation. So someone will do a numerical simulation to predict the physical conditions of a particular object. Might be a star, might be a cloud of gas, might be a whole galaxy, might be the whole universe, and then predict the intensity of radiation as a function of frequency coming out of that. And then the observers can compare their observational results with those predictions. If they agree, it's a viable model. If they don't agree, you go back, change the model and try and make it agree. Or you've got a model that predicts some new aspect that no one has observed before. And so you can use the models to predict what you might see and then propose to use a telescope to go and find it. That's the essence of how modern astrophysics works. And finally, I introduced these concepts of optical depth and brightness temperature, which are very useful. So the idea of an optically thick or an optically thin medium, and also very much used in radio astronomy is this concept of brightness temperature. So you can turn your measured intensity into a brightness temperature, and depending on what you think the optical depth conditions are, you could use this to diagnose the physical conditions of your object. That can be thousands of kiloparsecs away. Okay, so we'll stop there. And next up, we'll start on our journey of looking at different types of radio sources. And then in the workshop this afternoon, we will apply some of the concepts we've looked at in this lecture to the first of these types of objects that we're going to look at. Okay, let's stop now.